Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm very happy to introduce Cormac Flanagan, who's associate professor now at UC Santa Cruz. So he'll be here all of this week, and he's interested in talking to people to find out common topics of interest, looking for long-term collaboration. So I just wanted to say a few words about what Cormac has worked on in the past. I'll do a little reverse chronological order. So most recently has been working on checking concurrent programs, various kinds of properties like absence of races and atomicity violations and things like that. He also worked on static checking in the context of the tool ESC Java that some of you might have heard of, and automated theorem proving. And before that, he also has worked on type systems for functional programming languages in the context of his PhD thesis and in other work. Today he's going to talk about some of the work he did on checking concurrent programs.
Okay, thanks, Chaz. Yeah, so this is joint work that I guess I did together with Steve Friend and Chaz that kind of started when we were all back at this Systems Research Center many years ago, and that Steve and I have continued working on over the years. And the motivation for this is, let me see if I can get this right. Pretty much multi-threading has been around. It's always been problematic with the advent of all these multi-core processors. There's probably a lot of people here worried about the same kinds of problems, right? Multi-threaded software is very difficult to get right. We need to write more multi-threaded software to exploit these multi-core processors. And, well, we need multi-core processors because sequential single-core processors just aren't getting faster anymore. So we need to do something with all those transistors, multi-core processors, multi-threaded software, and all of the issues that come with multi-threaded software, right? There's this combinatorial explosion of interleavings. Testing is so much harder because it's very hard to get good coverage. So we have this whole motivation behind our study of multi-threaded code. Now, at the same time, writing software is always hard. Type systems, kind of traditional type systems, have proven really helpful at catching certain kinds of errors. You write in a type language, you never get errors at runtime that you called a method with the wrong number of arguments. All those things are called at compile time. So for certain kinds of errors, type systems have proven really well. So what we've been trying to do is trying to put these two worlds together, right? We want type systems not just for sequential software, but for all these kinds of errors that kind of crop up and are so insidious in multi-threaded software, namely race conditions and atomicity violations. Wrong one. So I'm going to try and illustrate these ideas pretty concretely. I know this is the right after lunch slot, and I was sitting in the audience here yesterday after I had a good lunch, and it was hard to stay awake. So I'll try and keep this interactive as much as possible. Some of you may have seen some of this stuff before, so feel free to speed me up if you've seen it. Feel free to ask lots of questions, and in return I'm going to ask you some questions along the way. So we'll keep things interactive. So as a running example for this talk, here is just a simple class. This is Java code, pretty much the same as C# code, more or less. A class that implements a reference cell. So we've got a field that contains the counter and a method to add 2 reference cells. We create 2 reference cells. X has 0, Y has 3. We add Y to X twice. And is X guaranteed to contain 6? This is the whole program. I see lots of heads nodding. Yeah. So this is fine. Usual stuff, we all know if we add in multi-threading, things get more complicated, right? And it's a little bit harder to reason about all the possible interleavings. But there's probably a number of you in the audience that are getting pretty suspicious about this assertion, right? Yeah. I see heads nodding, right? And the usual thing that's going on here is we have race conditions, right? Which I'll define for this talk. Fairly standard definition of 2 threads that access a shared variable at the same time and at least one of these axes is a write. So the two adds are both reading and writing to I at the same time. They kind of mess each other up. Maybe only one of them will happen depending on the interleaving, and there's lots of interleavings. And so this assertion might fail. So old stuff, how do we deal with it? Well, if we're good programmers, we put in synchronization into our code. So you might have something like this. Each thread will first acquire the locks on X and Y, and then do this method call. So here's the trickier question. Do you have confidence in this assertion now?
Yes.
So we have one yes. I think we have a few yeses. So yes, this code seems fine, and if we scratch our heads and stare at it for a while, we can gain confidence in that. But what we would really like, or what much of my research is on, is to say, well, listen, how would we develop type systems to be able to reason about the race freedom of this kind of code, right? To kind of automate this tedious reasoning that we're all kind of scratching our heads and trying to do right now. And for this kind of fairly straightforward lock-based synchronization discipline, it works out reasonably well. So as usual, we have code, it's in a type language, we have type annotations, we have int and ref and other things in various places. To have a type system for preventing race conditions, we throw in some more type annotations. So on field declarations, we say, this is a field, it holds integers and it's guarded by this lock, right? The implicit lock of the this object. And on method declarations, we say, every time you call this method, you got to provide a ref cell and you got to hold these two locks. Okay, so that's kind of what the programmer does, the annotation side of things. And then the type system, or you can think of it as the compiler, does a bunch of checks at compile time. Basically making sure that these annotations are followed, the synchronization discipline that the annotations describe are followed. So we have access to a field I. This check is pretty straightforward. I is protected by this. From the requires clause, I know we have these two locks. So this check passes. Okay, that's really easy stuff. The second check gets a little bit more interesting. So I is guarded by this, right? But when we're accessing this field, the this we're talking about is R. So we actually have to do this substitution over here to take care of the fact that the object we're really talking about is R. So R.I is indeed protected by R. That's one of the locks that's held at this point in the program. We know that from the requires clause. And so fairly easy kind of compile time check. Those two things hold. So provided this kind of requirement is satisfied at all call sites, we know that this method add is race free. Down below we have some similar kinds of checks. So what do we do here? We are going to call add. We need to have the locks this and R, right? But this and R are expressed in terms of kind of the formal parameters of add. So down here we need to replace them by the corresponding actual parameters, right? The this that we're actually talking about is X, and the R that we're passing in is actually going to be this argument Y. So we do the substitution on the locks that must be held. We check that these locks are held at this point in the program, which clearly comes from the synchronize clause. So this check passes. Another call side, same kind of check. And for kind of an idealized, nicely behaved subset of Java, we can have a soundness theorem that says if your program passes the type checker, then it's guaranteed to be race-free. Practice, things aren't quite so nice. You need some ways to escape from the type system when it proves too restrictive, much like you have casts in C. But for the underlying theory, it's nice to have this kind of soundness theorem.
So who is
Okay.
enforcing that I write down all the types?
The type system requires that.
So for each variable, I have to, for each variable in each method, I have to write this.
For each field, local variables don't get shared between threads, so it's not an issue. The second part of the talk then tackles type inference, which is how do we infer these things automatically, exactly for that kind of concern. Tom?
In this case, you need to know that the X and Y's that are mentioned in the two synchronized statements are really the same objects, right?
X and Y are different objects.
No. You have two synchronized. It could be that
yes.
somehow.
If you updated X,
Yeah.
if you said X gets Y, then all bets are off. Absolutely. And I kind of discuss the main themes but not some of the details. And one is that all of these lock expressions must be const. They cannot refer to mutable data at all. That's absolutely true. Okay, so this type system is very nice. It's a little bit basic and breaks down in some places. To give you a feel for that, here's a bit of a trickier example where I isn't protected by the this lock anymore. So this is a bit trickier. We have some extra lock M, and each of the two different threads is going to acquire M before doing this x.add of y. So a trickier example, same kind of question. Are we confident about this assert? Okay, I agree. And then we want to feed this into the type system. So we'll have to say int I guarded by what? So this is where it gets tricky. We'd like to say something like guarded by M, but M isn't in scope up there. And even if you could play some ugly tricks to make it in scope, you might have different clients of ref that have refs guarded by some other lock. So we kind of need to extend the type system to say not just talk about objects of class ref, but we need to say refs protected by lock M are refs protected by some other lock. So we add a notion of parameterization to the type system. Kind of like the type parameters in Java 5, but these are classes not parameterized by other types, but parameterized by locks. So when we declare class ref, we say, okay, it's going to be parameterized by some ghost lock G. Okay, so G is a variable. It doesn't exist at runtime, just at compile time, and that's why it's called a ghost variable. And we say, well, whatever G is, we're going to use it to protect the field I. When you call the method add, you better hold that lock, and you better pass in a reference cell that's also parameterized by the same lock. Right? So we're giving a more kind of flexible specification for this class. And then down here we can simply say, we have X and Y, they're both reference cells protected by M. And then the compiler is able to do the same kind of type checking reasoning as before. To give you a flavor of that, what we do here is, okay, we're going to call the method add. We better make sure that this lock G is held. And again, we'll take whatever that requires clause is. We'll replace the formal parameters this and R by X and Y. But the object that we're dispatching on, X, is parameterized by M. So we're going to replace the ghost parameter G by the actual parameter of the object X, which is M. Okay? So we do this whole substitution, and we'll say, the lock we really need to have when we call this x.add of y is M. And indeed, we have it. It comes from the synchronize clause. Okay? So these lock parameters, or ghost parameters, they add some complexity to the type system, but they give it a lot of flexibility too. You can encode things like thread local data in this way by saying, its ref is parameterized by some thread local lock. So essentially, once we had this type system, it was pretty good at handling most of the kinds of code we needed to deal with. Yeah?
I just wanted to ask, if in your experience, does it seem like the race conditions that exist in real programs come about from people making mistakes about which locks are held, or because they end up with aliasing that's uncontrolled? Because I'm wondering, like, this system depends upon freedom from aliasing.
Not really. I mean, it's sound even in the presence of aliasing.
You said the locks were constant.
Yes,
so
yes.
If it's mutable sort of memory things, at least then that wouldn't be constant.
If you...
So lots of mutable
right.
data structures would not work.
So a few things there. So mutation of lock expressions is different from aliasing, right? There are different kinds of causes of concern. Mostly the error comes from people just forget to acquire any lock. And there is this issue going on that we require that this lock expression is syntactically the same as this lock expression. And you could imagine, well, you'll call it M here, but we'll put it into some variable foo over here, and synchronize on foo instead of m, and then the type system would kind of not be able to reason about that aliasing. And that's certainly a weakness, and surprisingly, we never found that in practice. I mean, we kind of deal with this aliasing between formal and actual parameters by substitution, and that really seems to be almost all of what we need. This other issue of mutable lock expressions comes up from time to time. And it's kind of the corner cases we can't deal with, that's certainly one of them. Yeah, do you have a question?
So, while race detection is nice and lovely for races, some people program with races on purpose.
Yes.
How do you deal with that for a type state from a type state?
So that's kind of some of the escapes from the type system we talked about. On a field declaration, you can put in this annotation saying no warn. If you find races, don't tell me about it. I don't care. Or I know they're there. They're benign for some other reason. So those do come up from time to time too. So in our experience, by and large, this parameterized type system was enough to reason about race freedom on like 90% of the fields in a program. The downside was just the overhead of having to go through and figuring out all of these annotations. And so that motivated our work on type inference. Is there some automatic way to figure out all of these annotations? And it turns out when we first looked at this, if you don't have these kind of ghost parameters, it's fairly easy. It's like an n-cubed algorithm, pretty straightforward. But of course, ghost parameters, they are just, let me see, going forward. They are just necessary. So the problem we want to solve is given some mostly unannotated program, maybe with some annotations in there, can we do type inference to figure out all of these annotations, particularly in the presence of ghosts? And what we found out is this is surprisingly hard. It'd be nice if there was some monotonically converging algorithm we could have, but everything we looked at required making some choice, exploring something. If that didn't work out, backtracking, and trying some other choice. And so some kind of exponential time search. To give you a flavor of why that is, suppose somewhere in our type inference we find out that this check is violated, right? Does that mean we need to change this annotation up here? Or is this ref of m? Was that wrong? Should it be ref of something else? So that kind of gives you the idea of where we could get into this this backtracking search. So we tried, various kinds of approaches. None of them worked out particularly well, and eventually we, every algorithm we came up with was exponential time. We were feeling pretty dumb. And then we thought, well, hang on a sec. There's another common search problem that is only solvable by backtracking search. Propositional satisfiability. Maybe type inference is NP complete. And indeed, kind of discouraging, that turns out to be the case. If you take some SAT problem, you can create a program such that if you can do type inference for it, then that corresponds to solving the SAT problem. So at first this was a kind of negative result, right? It says type inference, boy, it's just really hard. But there's another way to look at it, which is that NP complete is not as hard a problem as it used to be. It's pretty funny, but over the past 5 years, people have made phenomenal progress on these fast SAT solvers, right? I don't know how many orders of magnitude they've gotten faster, but it's really substantial. So let's just leverage all of that hard engineering work that other people have done with heuristics and representations and all this stuff. And so the architecture we hit on was, well, we'll just take our program and find some way to construct a SAT problem for it, so that when we crank it through Chaff or whatever your favorite SAT solver is, and if it solves it, we can just kind of translate the solution back into type annotations for the program, right? We're solving an NP complete problem. Let's just use really good tools to do that, and put all of our stuff elsewhere. And once we hit on this architecture, everything else just kind of fell into place pretty easily. So the way this works is we do have some heuristic bound on the number of ghost variables for each class. Typically 2 or 3 works really well, because programs mostly don't need more than that. For this example, to keep it simple, let's use just 1. Okay, so the first thing we do is we put in these annotations with a bunch of unknowns, alpha and beta, alpha 1, alpha 2, beta. And the whole goal of type inference is to figure out what alphas and betas should be. And we're going to use a constraint-based approach. So we'll just translate this whole program into a bunch of constraints over alpha and beta. Okay, so for alpha 1, it's got to be some valid lock in scope. There's only 2 such locks at this point in the program, this and G. So alpha 1 has got to be one of those 2. Alpha 2 is the same. And beta is some set of locks that can only contain this, G, and R. So beta is some subset of those ones. Okay? And then for the body of the code, well, alpha 1 must be in beta so that we hold the right lock right here. And here, a little bit more complicated. If we take alpha 1, which is the protecting lock for I, but we need to say, but this we're talking about is R, and the object that we're looking at is going to be protected by, or parameterized by alpha 2. So we have these delayed substitutions in our constraints. Right? Earlier we knew what this thing was and we could just do the substitutions right away, but now we don't know what alpha 1 is. So the substitution just kind of sits around for a little bit. Okay, so we just need a solution to this constraint system. Now the key thing here is if you look at the first 3 constraints, we'll call them kind of scope constraints, they really bound the whole solution space, right? They just say, alpha 1 is one of 2 choices, alpha 2 is one of 2 choices, and this is, I guess, one of 8 choices for beta. So it's a very finite solution space. And we can encode that solution space using a bunch of Boolean variables. So Boolean variable B1 is going to decide what is alpha 1. Is it this or G? If we had more choices, we may need kind of a bigger decision tree, but it's the same idea. We'll use B2 to encode alpha 2, and then B3, 4, and 5 just say which of these 3 elements are in this set. B3 decides if this is in there. B4 and 5 decide for G and R. Okay? So if you give me Boolean variables, I'll tell you what the alphas and betas are. Okay, so now all that remains is to use this encoding to translate these remaining constraints into SAC clauses. And let's look at the second constraint, because it's kind of the interesting one. And so this is really just a bunch of kind of, at this stage, basic algebra. I'll just kind of work through it in a few steps just to keep everything concrete. So we have this constraint we need to solve. And we know what alpha 1 is. We have this encoding over here. So we'll just stick that in. And now this delayed substitution that was kind of waiting around for a while, now we can finally apply it, right? Because we know what this thing is. So we do that substitution, and so we get this constraint. B1 question mark R colon alpha 2 must be in beta. We know what these 2 things are, so we'll just substitute them in. And we'll get this big constraint. Not quite a SAT problem yet. But suppose B1 was true. Then this left-hand side must be R. So R must be in this set over here, so we know that B5 is true. So that's a SAC clause, right? If B1 is true, B5 is true. If B1 is false and B2 is true, this is the left-hand side, so B3 should be true. And again, if these 2 things are false, the left-hand side is G, so B4 better be true. And that's kind of the overall flavor of the system. Finite solution space, encode it using Booleans, translate the remaining constraints into clauses, dump them off to the SAT solver. Get that tool to do all the heavy lifting. So an overview of this whole system, just to see how it all connects together. We take unannotated code. We put in these ghosts and all these unknowns. Generate constraints. Pull up these Boolean variables. Encode the constraints as a SAT problem that then we feed to chaff. If we've been good and the program is well typed or is typable, chaff will kind of chew on things for a while, eventually say, yep, this is satisfiable. Here's a satisfying assignment. We can take the satisfying assignment that says B1 is false and stick it in right here. We lost that piece. But And it'll say things like, alpha 1 must be G, and we can stick those back into the source program, giving us a kind of explicitly typed, well-typed program. So that's in the good case. In the bad case, the chaff sat solver will say, wait, this problem is unsatisfiable. And then we know that the program is not well typed. And in fact, what we do is we generate a separate SAT problem for each different field declaration in the program. And so if this SAT problem comes back as being unsatisfiable, we know there's a race condition on this field. And then we have variants of this that instead of generating kind of this SAT decision problem, actually generates a max SAT optimization problem, with the idea saying, even if you can't find protecting locks for everything, give me the best guess at a lock that's used in most places in the code. Yeah.
So what is the algorithm exponential in? Is it the size, maximum size of any method in the program?
Worst case, we haven't really done a precise worst case analysis. All we know is it's exponential in the size of the program. In practice, it scales quite well, because I think the SAT problems we generate are very straightforward, and they can just be...
Do you also generate constraints between Boolean variables that correspond to one method and another method? Because the example that you had, the constraints are only being generated between the Boolean variables for one particular method.
So it is quite plausible that you'd be able to do a better worst case analysis. We haven't really done that. We also only know that this type inference problem is NP complete if you need at least 3 ghost parameters, because kind of your 3 SAT clause gets translated into 3 different ghost variables. So if you only needed 2 ghost variables, we don't actually know that it's NP complete. So this works. It's kind of disturbing that, there's potentially a worst case exponential algorithm sitting in there. But in practice, we've run it on a bunch of benchmarks, kind of from pretty small things up to JBB. And these are kind of semi-standard benchmarks for kind of the race condition literature for Java. We did put in some annotations by hand in these benchmarks. For example, to say, in this part of the program is single-threaded, and so you don't need to worry about synchronization. We also have a separate analysis to reason about thread local and read-only data, which of course doesn't need to be synchronized. Yep.
What is that annotation? This part of the program is single-threaded. How do you say that in the tool?
You'd need to ask Steve for all those details. He's been doing all of the hands-on work. I think it's something like / ampersand single-threaded.
So you basically, it's like a begin and end.
Yeah, just some statement in the program you say, I'm single-threaded right here.
Oh, okay.
Right. And it's moderately easy for a programmer to see that, but it's not something the tool can infer. But this is, a few per 1,000 lines of code. So in terms of inference time, the tool isn't blazingly fast, but it's tolerable. It's typically about 10 seconds per 1,000 lines of code. Noticeably worse on JBB, but this still terminates in under an hour. So, certainly usable. And more interesting is, on all of these benchmarks, we're able to prove that upwards of 90% of the fields are race-free. So it's kind of saying, if you're worried about race conditions, you only need to worry about some small fraction of the fields in the program, because everything else we can kind of crank through automatically. Okay? So that's, yeah?
So the inference is done always on the whole program, but one at
Yes.
a time, sort of.
Yes, yes, yes.
That you're just generating all the logical formulas related to one
Yes.
field and then try to do something.
Yes.
But it's basically means that you cannot do this analysis so one class at a time, in the sense that you cannot get the most general type sort of for a class.
Yeah, we have really developed this as a whole program tool. If you had private fields, you might be able to do some kind of more modular analysis. Or you can imagine putting in all of these type annotations at your boundaries to a class or a package, and then just using the tool to infer things within that, say, class.
So, but if, for example, you have some piece of code,
Okay.
and you do this analysis there, now there might be there's another piece of code, perhaps it's dynamically loaded or something, I don't know.
Right.
And that accesses a field without holding a lock. So that would
Yes.
violate it, right?
Yes.
So you imagine that
Right, it would be some kind of compositional reasoning, right? You can verify this is race-free, but there's obligations on your environment. If you dynamically load code that violates that, then all bets are off. Yeah?
So did you look at the fields which this tool could not prove race-free? Like were they real races or?
Some of these have real races. I don't remember offhand. This was almost too big to look at. It's very hard when you go into a big code base to try and figure out. You say, I don't see any obvious synchronization on this field, but maybe there's something really subtle going on that I just can't understand. But I think certainly many of these are real races. And I think there are a real race in Ray Tracer as well. The paper on this has all of those details. Yeah.
Have you run any benchmarks on other race detection code for Java?
Other people have.
Yeah. You find similar races in those?
By and large, yeah, the races are similar. There's some differences. Yeah.
So when the set solver returns satisfiable, it provides you a concrete instance, right?
Yes.
How reasonable is that if you have multiple instances that could make it satisfiable, you're just choosing one, right? Does that?
This is because we have different SAT problems for different fields. Right, so if we have two different fields, we'll come back with two different sets of annotations, and we can kind of just stitch those together. Basically, if to prove this field is correct, we need to say the class is parameterized by one thing, and to prove this is correct, the class is parameterized by another thing. Then we say, okay, the class really must have two parameters. One that protects its first field, a different one maybe that protects its second.
So you'll have as many parameters as the number of fields in every class?
Conceivably, yeah.
I mean, you will, because you have no way of unifying those, right? Because you're solving each problem separately, then how do you unify the parameters?
Well, if the parameter isn't used in some solution, say to prove that field I is, if there's no races on field I, if it doesn't use a parameter.
Oh, then you can run.
Yeah.
I see, okay.
Yeah, so there is that whole step of stitching those things together. It's a good point. Yep.
Andrew, I don't know anything about this. Are there runtime race detection tools that you can use which annotate only the 3% of fields which you couldn't be sure about here? And then simulate the program lots of times to see if it does produce races from those?
So, yeah, there's lots of dynamic race detection tools, and you could try and focus those on these. Or conversely, you could try and use this kind of static guarantee to optimize those other dynamic race detection tools. And people have looked and made pretty good progress on kind of a synthesis of static and dynamic checking. Basically using this kind, well, not this kind of static analysis, but static to optimize the dynamic analysis. Yep.
So a lot of the complexity comes from this ghost parameter, right?
Yes.
So what if you simply suppose you have a global naming mechanism where you can distinguish different logs, for example, by looking at the type of the class and the rank, etc., and just use that common thing as a global log, if you will, then you don't need this ghost parameter, right? So how essential is it to introduce the ghost parameter?
So in Java code, I guess a lot of stuff has really fine-grained locking. You really do use an unbounded number of locks. And so some abstraction or approximation that just thinks in terms of a finite set of locks.
So for example, the log m, if I just look at the type of that class,
yes,
and use that as a unique identifier for the log, would that be sufficient?
So it would be unsound because you could acquire the one m and then access fields of another, which is kind of the difficulty here. That's why we need all of this complexity. It's kind of domain specific. You do have some domains where, say, embedded systems, where typically you just have a finite number of global locks, and then all of this stuff goes away. Things are a lot easier. But in the Java code we were looking at, really that's not the case. Most data structures are very fine-grained locked. There's lots of little local locks around the place. Yep.
in the annotated code that comes out of the inference engine, how much bigger is it than the original piece of code? Like, how many extra characters are you adding to the program?
I would guess roughly there's an annotation on every field declaration and every method declaration. So that would be pretty modest in terms of percent overhead. I'm guessing something like 10%. Yeah. Okay.
You said the analysis, the inference for unparameterized type system is pretty straightforward, right?
Yes.
So have you tried this on this benchmark and seeing how many fields can be verified race-free on that one? Because I'm worried about the unnecessary parameterization in the sense that if you have just one bug or some whatever type in one function, it will pollute a lot of classes, making an extra parameterization.
So the worry there is that you get lots of false alarms, and all the good stuff will be so buried in the false alarms that it would not have much value. We kind of did that by saying, let's parameterize it so we have no ghost parameters per method. And I can't remember offhand, but they were significantly worse. Yep.
So you're running, run the three-sat solver. Sometimes you say yes, it verifies.
Okay.
Sometimes it says no, it doesn't verify. But you've mapped it into this three-sat space.
Yes.
How hard is it to unmap the? Usually you get a counter example at that point. How useful are the counter examples to actually say, how do I find this race in my actual code?
So the first thing is a separate sat problem says the race is somewhere on field I.
Right.
Second is we have this max sat problem that says the race is on field I, and hey, the lock this protects most accesses to I, and doesn't protect the ones on lines 34 and 37.
Okay, that's the part.
Right, and this is just a guess.
So
yeah.
Max sat, well, at least you can reverse translate these results pretty easily.
It'll give you its best guess at a protecting lock. Yep. So all of that is on race conditions. And I remember when I was giving an early version of this talk many years ago, this guy I worked with, Andrew Burrell, who did a lot of work with multi-threaded codes, asked me more or less this question. If we take something, this is a variant of the reference cell, so it has an increment class and it's internally synchronized, right? So if this is obvious stuff, just kind of tell me to speed up a little bit. But basically the idea is this method has two properties. It's race-free, and it behaves correctly in a multi-threaded context. If you call inc from multiple threads concurrently, they all work just fine. And many programmers confuse these two and think they're synonyms, right? And Andrew's question is, well, what about this method? This is a different way to write increment. And this is clearly race-free, right? Every time you access I, you have the lock, so you never have concurrent accesses to I. Yeah?
What is the definition of correctness here?
So the definition of a race condition is two simultaneous accesses to a variable by different threads.
Correctness, so...
There's no definition.
I'll get to it on the next slide, but right now you can intuitively know that increment behaves badly if you call it from multiple threads, right? There's a window of vulnerability between these two critical sections that if somebody else comes in and says, I'm going to increment I, that increment is going to be overwritten right here. It's going to be completely ignored. So I think intuitively we all agree this is incorrect code.
It seems a strange definition of race-free. I would be inclined to redefine race-free to say race-free involves a get, then a set, then another set event.
Absolutely. And so there are different definitions of race-free. So I was careful to give one particular definition for this talk. So in that notion of race freedom, this is clearly race-free but erroneous. And so kind of the same question comes up, what is the right definition of race freedom? Or what is the right definition of to behave correctly in a multi-threaded environment? Okay? So race freedom does not prevent errors due to unexpected interactions between threads. And so in some ways the right definition of race freedom is what is often called atomicity. And so a method informally is atomic if other threads don't interfere with its behavior. More precisely, it really means kind of serializability, right? So here we have some arbitrary interleaved execution of this increment method, right? So it acquires a lock, reads I, updates I, and releases the lock, and there's another red thread doing some arbitrary other things. We don't know quite what it is. And there are lots of different kinds of interleaved executions, right? So atomicity basically means for every interleaved execution, there's a serial execution with the same behavior, where the instructions of the increment method are all executed contiguously without any interruption. Yeah?
Sorry to interrupt.
Yep.
I would have observed that that's idempotency, not atomicity.
It goes by different names. It's the same as serializability or linearizability.
A little bit different, right? Idempotency is the statement of serial execution observed from the outside, regardless of what may have happened on the inside, whereas atomicity is do it all or do none of it. That's the way I would have viewed that.
So atomicity in the database literature has a different meaning, unfortunately.
Yes.
What they would call serializability, the programming language literature calls atomicity.
This is really what in the database literature is called isolation.
Okay, thank you.
Okay.
Thank you for the translation.
Okay. So yes, I'll rename atomicity as need be. And I'm sorry for the confusion. It's just kind of a collision of terminology. So if we can prove this, it's great, right? Here there's all this exponential combinatorial explosion about different kinds of interleavings. Here we just have to reason kind of about the sequential behavior of increment. So if we can prove atomicity or isolation, reasoning about program correctness gets a lot easier. So yeah, also known by different terms in different domains. Key benefit is that it enables sequential reasoning. So that's all kind of old stuff. What's interesting here is it is a surprisingly good match for the way people write existing code, particularly Java code, which is where all our experiments are in. And 80 or 90% of the code in existing multi-threaded programs are atomic. And you look at the Java doc specifications, and really programmers are thinking of it this way. They say this class is thread safe, roughly translated as all of its methods are atomic. And the other interesting thing is atomicity, like race freedom, is fairly amenable to being kind of verified in a type system that you could check at compile time. And the key aspect of this type system, or the key reasoning that it's doing, is based on Lipton's theory of reduction. How familiar are people with that theory of reduction, or should I review it? Okay. So it's a really nice argument. The key thing it leverages on is the knowledge that the field I is race-free. So here we have some arbitrary interleaved execution. And if we know the field I is race-free, then we know that whatever Y does, this thing of some other thread, it's not going to access the field I, because that would be a race condition. So these two operations, they commute. Doesn't really matter what order these two instructions get done in. And I could say, hey, here's a different execution. They're interleaved in a different way, but you have the same final state, right? So that's the first step. Now we acquire the lock. So the blue thread has the lock. I don't know what the red thread is doing, but it cannot acquire the lock because some other thread has it. Can't release the lock because it doesn't have it. So these operations can't really mess with the lock at all. So those operations commute. Does that make sense? And the same kind of reasoning applies here. The blue thread still has the lock, so whatever Z does, it can't mess with the lock. And these operations commute. And so by this kind of commuting argument, Lipton was able to show that for the increment method, provided there's no race conditions on I, increment is atomic. It's serializable using this commuting argument. So that's really neat. How do we do this in a type system? So we already have ways to reason about race freedom. So that's key. And if we have a race-free variable access, we can commute it either way, right? In this case, we choose kind of to push this operation over to the right. But we could also push it over to the left because X cannot be accessing I either. So race-free operations commute either way. Acquires, we can always slide to the right. And releases, we can kind of slide to the left. So we just need to, when our type checker or compiler is looking at the code for increment, it just needs to check, there's a bunch of things that slide to the right and a bunch of things that slide to the left. And if there's one operation in the middle that doesn't slide at all, that's okay. So the type checker goes over all of the paths in the method, And for each operation along one of those paths, it assigns it one of these atomicities. Either a right mover, something like a lock acquire, a left mover, something like a lock release, a both mover if it's a race-free variable access, and if it's a conflicting variable access, it says it's atomic. It doesn't slide either way on the kind of transparency at all. Okay, so if the type checker is looking at this execution path, acquire, read, write, and release, it says it's a right mover, a both mover, and a left mover. And then there's a bunch of rules about how you combine these different atomicities. So if you have a right mover and a both mover, kind of intuitively you can see that the whole thing can move to the right. So that is still a right mover. So right mover, both mover, this is still one right mover. We add on another both mover, this whole thing is still a right mover. And if we have a right mover and a left mover, the whole thing is atomic. So it looks at this code path, it says, oh, I have different kinds of movers, I just put them all together, and I can infer that the whole code path is atomic. And it just does that over all of the code paths, or more properly over all of the kind of the things in the abstract syntax tree. Okay? So if we look at the bad version of increment, this is an alpha renamed version of increment that's now called deposit, but acquire, read, release, acquire, write, release. It's a right mover, both mover, left mover. This whole thing is atomic. We have the same critical section over here. It's also atomic. But if you try and compose two atomic sections together, we get this atomicity compound saying, wait, there's no guarantee. I mean, other threads could interrupt here and do strange things. And in particular, that's exactly true. Other threads can come in here and kind of override balance. Okay? Is that making sense? So you've seen some of these atomicities, but they're not always quite enough. So here we have a deposit method, as much as we've seen, and we have this method deposit twice, that calls deposit twice. And let me throw out this question to you. So we've already seen this kind of method, and we know it's atomic. How about this method? Is it atomic? Yeah, indeed it is. But if we try and feed it through the type checker, what the type checker will think is, well, of course, deposit is atomic. Deposit twice has various things, including a call to deposit that's atomic, another call to deposit that's atomic. If we sequentially compose these two things together, we get compound. And so the type checker will complain about this method. So that's kind of not good, right? We have some correctness argument that deposit twice is atomic, but the type checker cannot prove it. So we need to beef up the type checker a little bit to be able to reason about this. And the key thing that's going on is we need a more precise spec for deposit. It's not enough to say it's atomic. I mean, certainly it's always atomic, but what if it's called when the lock is held? Exactly the situation here. So if the lock is already held, Java has reentrant lock, so this lock acquire, it's really a no-op, right? So instead of this pattern, suddenly we have a whole bunch of movers. Altogether, it's just the same as mover. So what we're seeing is if the lock, this is held, deposit is a mover, otherwise it's atomic. That's exactly the kind of spec that we need to put down. So we add those kinds of specifications to our atomicity type system, basically saying if the lock, this is held, the method's a mover, otherwise it's atomic. We go down here, and that's the spec for deposit, but in this context, the lock is indeed held, right? So we do a bit of reasoning, and we say, we have a lock acquire, a right mover, a both mover, a left mover. The whole thing is atomic, and the type checker is happy. You can verify atomicity. Yeah?
How rich can you allow this language of conditional atomicity to be and still be able to check it?
Okay, so these can be arbitrary things. So you can have kind of complicated nested decision trees. You can arbitrary atomicities. And the lock expressions can be any Java expression with the requirement that it must be const. It must always evaluate as the same thing and cannot touch any mutable data. Right? If it can only touch final variables and final fields. And then there's a caveat that final fields aren't quite final because of initialization, but I'll punt on that a little bit. Okay? So if we apply this to things, we applied it to a whole bunch of kind of standard Java libraries that are supposed to be thread safe, and found a bunch of interesting things, and this is kind of illustrative of it, right? So the increment method with the synchronized blocks, right? That's a very artificial example. But you kind of throw in one level of indirection through a method call, and you get lots of examples like this. So here we have a constructor for a vector that just takes in some collection C and is supposed to initialize the vector with the contents of that collection. So it calls c.length to get the length of the vector, which is an atomic method. It then allocates some space to store that data, and then it calls c.toArray to copy in all of that stuff. And the type checker said, well, this is atomic. Sure, allocation is a both mover. It doesn't mess with other threads. But toArray is also atomic, so it said this whole method is compound and complained. And we went in and looked at this, and we said, well, you know, this is absolutely right. We could call count to get the length of C. Then some other thread could say, hey, I am going to make C bigger. I'll add to that collection. We come down here and we call c.toArray, except because C has gotten bigger, data is too small. So what does toArray do in that situation? It says, the array you gave me was too small. I'm going to allocate a new array to copy my stuff into. I'm going to return that new array to you. And that returned array is dropped on the floor, meaning that data is still 0 initialized. And you get kind of some weird behavior down the road when you suddenly have this vector that was never initialized with the collection it was supposed to be initialized with. So we get kind of lots of corner case errors like this that would be very hard to catch using testing. So I am a little bit out of time, so let me try and wrap up very briefly. So of course the same issue comes up. You have a whole bunch of legacy code, you have a nice type system to reason about atomicity, but it's a pain to write the annotations. You really want type inference. And type inference turns out to be a much easier problem. We kind of have a constraint-based type inference algorithm. No exponential time, no SAT stuff or anything like that. Kind of at each method, we have this lattice of possible specs for the method. Const means, boy, I always return the same thing. Mover says I don't interfere with other threads. We've left and right movers. We have conditional atomicities that we've seen that we need. Some methods are atomic. Other methods are compound. They interfere with other threads. And even beyond that, we have methods that are error that say I violate the locking discipline. And it's bad if you get any of those. We have a whole constraint-based type inference algorithm. And the performance of this algorithm in comparison to the race-free type system is quite fast. So it's maybe a second or two per 1,000 lines of code. JBB, let me see. Yeah. So basically, even for large programs up to 30,000 lines of code, it's about seconds. More interestingly is how precise it is. So within these various benchmarks, for most of them, it was quite nice. We were able to prove that about upwards of 80% of these methods are atomic, which means that for 4/5 of your code, sequential reasoning is just fine. Right? There's this little gap at the top where multi-threading really comes into play, and you need to do more complicated things. But most of the time, you're still living in a sequential world, and we're kind of able to kind of isolate that sequential world within multi-threaded software. TSP is noticeably worse, and what's going on there is kind of this, I think what's called a branch and bound algorithm. You have a bunch of threads looking to solve an optimization problem, and there's a global variable that says, this is the best solution I've found so far, and everybody's kind of racing on that variable. But they're benign races, but you do need to worry about all these interactions of threads. We also looked at a bunch of classes that were documented as thread safe. And again, similar kind of things, upwards of 80% of these methods we could verify as thread safe. Here the interesting thing was with printwriter, which is kind of a wrapper around an I/O stream. What these warnings were complaining about is essentially saying, well, you had some I/O stream that you passed as this constructor for print wrapper. And I know print wrapper always holds a lock when it writes to that I/O stream, but I'm worried somebody else might keep an old handle to the underlying I/O stream and write to that without the lock. And so that's really what these warnings are about. And it's kind of a valid concern, right? So you call println on a print writer, and it prints the string, but then there's another thread that does something to the underlying stream and inserts some characters, and then you get the new line, right? So println really wouldn't be atomic in that situation. Okay, and then the last part. So what we've seen is a type system that you'll give code like this. It'll infer some atomicity annotations, and here the user specified in the original program this should be atomic, and the type system will say, wait, no, that's not the case. But of course, as soon as you get an error like this, you say, boy, well, I guess I need to figure out what the right lock is. I need to go in and insert all of that lock, insert the synchronization code. So we've also been playing with synchronization correction. The idea is saying, you don't really, I guess when you get this error message, you want a quick fix button that says, does this automatically for you. It kind of looks at your code and says, wait, your synchronization wasn't quite right here, and put in extra synchronized clauses as necessary. So the kind of constraint-based inference algorithm to infer atomicities, we've extended to also infer when things go wrong, what synchronization could have been put in there that would make things okay. Yeah.
Does your atomicity inference system infer conditional atomicities?
Yes. Yeah. Yeah, there's a whole bunch of details that I kind of ran out of time on. Yeah.
What about deadlocks?
So here's the thing. It'll introduce enough synchronization so that this method is atomic. You probably want to worry about deadlocks too, and that's just kind of an orthogonal issue that we don't really deal with. Maybe you want to eyeball it and say, yeah, that looks right. Maybe you want to use some other deadlock detection tool.
Or you could deadlock the entire program at the start of main, and it would have no race conditions.
That is true. So the deadlock is certainly an issue. So we didn't deal with that. There are other tools that do. It's, in our view, an orthogonal issue, but important. What we did do is we took a bunch of classes, standard Java library classes, and we said, well, suppose we insert a couple of bugs in there, basically saying, going in, removing synchronization. How well will our tool do at automatically kind of fixing those bugs? And so by and large, and here, if we just insert one bug, we do a whole bunch of samples. We say, how about if we remove this one? How about if we remove this? How about if we remove this? If we just insert one bug, by and large, it works pretty well. 2 bugs, it's a little bit worse, and 5 bugs, it's still doing okay. String is mostly an immutable class. It doesn't have many synchronized statements in there. It doesn't even have 5 of them. So we couldn't run that experiment. So this is showing that this works reasonably well as long as you don't have too many synchronization errors. If you've lots of synchronization errors, the max SAT problem cannot even conjecture a good protecting lock for your fields. And that's kind of where things go wrong. It's kind of starting to happen in places like this. Okay, so I'm at the end of my hour. So that is about it. So type inference for race conditions with these ghost parameters turns out to be NP complete. But by leveraging advances in SAT solvers, this seems to work pretty well up to as far as we've pushed it, about 30,000 lines of code. And can verify over 90% of fields as race-free. We've also extended this type-based approach to atomicity. And even on moderately big benchmarks like JBB, we can prove that 80% of methods are atomic. And some progress on synchronization correction, kind of more on a class local basis for thread-safe classes. Yeah?
So given that you can do this analysis and you can find out in these programs that most of the program is atomic anyway, did you see the need for software transactional memory?
So I hate software transactional memory, and I love it. The reason I hate it is it makes all of this work redundant, right? You put atomic in there, and boy, you're done. Yeah. My philosophy is I can see reasons to reason about threads and locks explicitly, low-level stuff, right? You don't want the overhead of transactions. If you do have transactions, threads and transactions seem to me to be a funny thing, right? It's kind of high level in terms of transactions, but I don't like threads anyway. Maybe you want kind of thread level speculation or something like that, something that preserves a more sequential model of programming. Maybe if you have a domain that's amenable to map reduce, that's a great model to program in. Transactions to me seem a little bit like C++, trying to span a huge abstraction boundary from high-level objects down to low-level bits. Right? Transactions are high-level, threads seem kind of low-level for many applications. And of course there's this issue, sometimes you have threads because your application is naturally threaded, a web server. And sometimes you have to force threads in just to get all the cores to run. And the second kind of threading is a thing that, in an ideal world would go away. So that's a bunch of rambling thoughts in answer to your question.
So okay, second question. Assuming that this kind of set of tools are deployed widely, and people write a lot of code now in Java and C#, the claim is that race conditions and getting multi-threaded programming right is hard, and you spend a lot of time on these related bugs. Do you believe that would be true if you had the tools in place?
I guess we've got all the low-hanging fruit, right? We can prove 80% of the methods are atomic, that's fine. And the remaining 20% is, it's still going to be hard. And you need some other approach to tackle that. And testing won't quite do it, and you could try code inspection, and that would probably be pretty good, but very time-intensive.
But the difference is that now people don't know that this 80% is
absolutely
atomic. And this,
yeah.
So that gives you factor 5 right there in terms
yeah.
of the amount of effort that you would put in.
Yes.
So that seems pretty substantial. I mean, in my opinion. In terms of leverage over solving this problem.
Absolutely, right. Yeah. So it certainly gives you a lot of leverage. Yeah. The stuff you kind of felt was okay, now you know is okay. And the stuff you were always worried about, well, you're still worried about it. So yeah, it gives you a lot of advantage. I don't know if, it makes the problem smaller, but it doesn't go away. So yeah, maybe we should chat offline about transactional memory too. Yeah.
How do you deal with block-free programming, even if it is atomic block-free programming?
We will say,
for example, Lamport's bakery algorithm.
We will say we cannot verify this method is atomic. And you can go in and you can do things like declare a method as atomic and put a no warn on it. And then the type system will just assume it's atomic. But you better be sure you're right, because everything relies on that. Yeah.
Okay, so this is another related question. So if you had, again, if these static race detection tools were available and widely deployed, do you think there'd be really much need for dynamic race detection tools?
Yes, again, for that last 10%.
Okay. But it would get rid of a lot of the problems that we currently have.
Yes. Yeah. Yep.
So you mentioned you need to add some annotations for thread local kind of property. So
yes.
Some of them, I imagine, would involve a call stack that uses synchronized keyword, right?
Yes.
Some might be the case where in the path you don't use synchronization at all, but yet it should be under multi-threaded environment. So do you have an assessment like, what's the percentage of those cases? So I think my real question is that if I just follow the path and to see whether it uses synchronization at all and use that as the heuristic to say whether it's single-threaded or multi-threaded, would that be sufficient?
So the single-threaded versus multi-threaded, I'm sure there are. So we haven't really tackled that problem. We just put in an assertion that it was and leveraged it. And I'm sure you could come up with different kinds of static analyses to do that. It's just we haven't done that.
So actually, I have a question.
Yeah.
In the type inference for race freedom.
Yes.
the results you reported for how many fields you were able to verify race-free were with respect to a certain number of annotations.
Yes.
If you started out with saying all annotations are prohibited,
yes.
How good would those numbers be with your analysis?
They would be worse.
How much worse?
Probably a factor of 2.
So then you would be able to not verify race freedom on 50% of the fields.
I don't remember offhand. That part of work was done about a year ago, but that could be ballpark.
I see.
Yeah. But the number of annotations there to me doesn't seem to be excessive.
So by the way, how many? If you actually said that, okay, you actually have to do so many annotations that you would have done in the previous type system or without any inference. I'm just wondering, what is the cost of annotation, relative cost of annotation? I mean, if you're allowing annotation, you might as well say that just do the whole damn thing and do only type.
I think it brings down the overhead by about a factor of 10. It's about 1 annotation per 1,000 lines of code versus maybe 1 annotation per 10 or tens of lines of code. Probably more like 1 every 10. So yeah, there's a lot of leverage there.
What is the annotation burden for the race freedom type system compared to the annotation burden for the atomicity type system?
Boy, that's a good one.
Both with the versions with inference.
Steve would have all of the details on that because he was the one who had to go through and put them in by hand. I am guessing that in some ways the race freedom is the harder thing, and they would be somewhat more.
You would first run the race freedom type inference before you run the atomicity type inference.
Yes. Yeah, that's the way it all works.
Won't do anything.
Yeah. And I don't think there were many or extra ones needed for the atomicity type system at all. It was all at the first step to verify race freedom.
You don't need to. Well, in your examples, you had marked methods as being atomic.
Yes. So very good point. I was a bit remiss in skipping this. So what we're doing here is we are basically going in and not by hand, but inside the tool saying, try and prove every method's atomic. And if not, give us a warning. Because we didn't really write the code, we don't know which ones should be atomic. So of this gap here, maybe there are some methods that should be atomic and there is an error in the code. Maybe it is atomic and we cannot verify it. Or maybe it's a method that the program never intended to be atomic, like main, right? And we were just foolish to try and prove it was atomic anyway. And I'm not exactly sure how this gap divides into those 3 categories. Here, we're a lot more confident that really all of these methods were intended to be atomic because they were documented as being thread safe. And so this is likely either errors or approximations in the analysis. And some of them are indeed errors.
So for that, there's no annotations?
No. Other than this kind of annotation on the side, this heuristic that says everything should be atomic. Yep.
How incremental is this approach? After you infer some annotations and then programmers come in to say that, this is too complicated a set of annotations, I will correct it this way. And then later we'll do inference again to, like, when the code gets modified a little bit.
Yeah, as implemented, it's a whole program analysis. And if you change the code, well, you do the analysis from scratch.
Already inferred.
Yeah, and you could imagine kind of restructuring this to be an incremental analysis. And that's kind of a step down the road. I guess our first thought was to say, let's implement it and see if it actually works. And later on, try and make it fast.
Are there incremental SAT solvers?
There are, yeah. And in fact, we use them in part because we have a bunch of very similar SAT problems. The first one trying to prove field I is race-free, and then we prove field J is race-free, and we've experimented with using the incremental versions of SAT solvers with some benefit there. Okay. Well, thanks for your attention.